Hello everyone and welcome back to Causality with Boris, broadcast from SobolevSpaces. In this video, you'll learn how to find implied association in DAG. There are three main things in the video: identifiable treatment effect, graphical identification rationale, and adjustment criterion. Make sure you watch till the end for some revealing examples of graphical adjustments. And the takeaways. Compare them with your notes. As always, I prepared a PDF that goes along with this lesson. Check out the link in the description, and the PDF will be sent to your inbox. DAGs encode assumptions about variables, direct influences, network of influences. Some assumptions come from the literature. Some are our conjectures. Still, we view DAG as a set of assumptions, and they are accepted as certain to happen. We use these assumptions to derive associational implications, marginal and conditional independence, and spurious associations. Consider three variables connected by immediate influences, and two of them are unconditionally independent. There is no error between them. We have two simple rules. Common cause makes dependent two independent variables. Conditioned on their common cause, they stay independent. On the other hand, common effect works in the opposite direction. Two independent variables will be dependent in a stratum of their common effect. Let's bring the Markov assumption. It goes beyond three variables in the immediate circle. The assumption states a variable is independent of any other variable conditional on its parents. The d-separation moved us even further. Just to remind you about d-separation. Blocked paths don't transmit variation. Unblocked paths may transmit variation. And here is the three criteria to find out if a path is blocked. 1. Conditioning on a collider blocks a path. 2. Conditioning on a collider opens a path. 3. Colliders block a path. And now two associational implications of d-separation. X and Y are independent given a set of variables z if z d-separates them along all paths between them. In other words, given z, the joint probability for x and y coincides with the product of their univariate conditional probabilities. We can say that even shorter. Outcome doesn't depend on treatment when z is constant. Conversely, x and y are not independent given z, if it doesn't d-separate them along all paths. The joint probability for x and y is not the product of their univariate conditional probabilities anymore. The phrase given z, it's a mathematical shorthand for saying after conditioning on z. In this context, conditioning means stratification over the strata defined by combinations of values of variable in z. Interested in marginal and conditional independencies? You can read them all of the DAG. To do this, use the d-separation criterion. That's a quantum leap forward in causal reasoning. Now we have a criteria to say if treatment effect is identifiable purely on the basis of qualitative assumptions. Assumptions that are encoded in a DAG. You'll be amazed to learn that criteria work even if you don't know the functional form of the effect connecting nodes, because they are graphical. Here is the rationale for graphical criterion. If we can block all non-causal associations between x and y, then remaining association is causal. We conclude effect of x on y is identifiable. Let me walk you through this reasoning step by step, and I'll use treatment and outcome instead of x and y. First, a path which d-separates treatment and outcome. It doesn't produce an association between them. Second, treatment and outcome are d-separated along all paths. Then there is a conditional independence between them. A stronger statement. Next, conditioning d-separates treatment and outcome along all non-causal paths. and it's not blocking causal paths between them. Finally, our identification rule. To identify treatment effect, we condition on variables that deseparate treatment and outcome. Deseparation is a great achievement. Its rationale underlies all graphical identification criteria. Most criteria give sufficient conditions. They determine if a treatment effect can be identified. That is, the treatment effect is identifiable only if some variables meet a certain criterion. Yet effect can be identifiable even if sufficient criterion is not met. Some graphical criteria provide necessary conditions. They determine when a treatment effect cannot be identified. But only Pearl developed a complete identification criterion. It detects all identifiable treatment effects, causal effects of treatment. Causal inference is often equated to covariate adjustment. Association between treatment and outcome is explored in the presence of other variables. Adjusting is also called conditioning, controlling, or stratifying. Here is a problem. You can adjust for every covariate inside, but still may fail to remove all confounding bias. It may even introduce new biases if you adjust for colliders or mediators. Graphical identification criteria guide the choice of variables. Let's delve into the graphical approach to adjustment. There are causal and non-causal paths between treatment and outcome. Adjustment variables must block all non-causal paths between them, but without blocking causal paths. Remember, if we block all non-causal association, only the causal association remains. Then the treatment effect is identifiable. If variables meet the adjustment criterion, then this is accomplished. Here is one way to interpret this with DAGs. A set of variables block all non-causal paths, and it doesn't block any causal paths. Equivalently, it deseparates treatment and outcome in all non-causal paths, and leaves them connected through all causal paths. So informally, the total effect of treatment on outcome is identifiable if adjustment for some variables block influences of all other variables except treatment. A formal proof of the adjustment criterion was done by 𝗕𝗂𝘂𝘶𝗵 in 2010. Consider the total effect of x on y. Let z be a set of variables, and we say z satisfies the adjustment criterion if two conditions are met. Holding z constant blocks all non-causal paths. That's one. No variable from z lies on a causal path or descends from it. That's two. That's it. Let's say z satisfies the criterion, then the total effect is identifiable by stratifying on it. The adjustment criterion is complete. It points to all variables that we need to adjust for in order to identify the treatment effect. But it may be empty. Is treatment effect identifiable? Now this question is meaningful. We see a network of immediate effects encoded by DAG. We recognize paths between treatment and outcome, some causal and some non-causal. Then we ask, is treatment effect identifiable by conditioning on variables in non-causal paths? This figure illustrates the application of the adjustment criterion. Its focus is on the effects of treatment. As always in this course, X is for treatment and Y is for outcome. Four distinct paths connect X and Y. There are two causal paths, a chain X to T to C and to Y, and a putative direct effect X to Y. Together, they graphically represent the total treatment effect. The other two paths are non-causal. According to our reasoning, they need to be blocked. One non-causal path is already unconditionally blocked. It contains a collider. It's a chain from X to A through T, combined with a common cause B for nodes A and Y. A is a blocking collider. The other non-causal path is U to X and U to Y. It's open but can be blocked. To do this, we condition on U. the adjustment criterion also points to B. It doesn't lie on or descend from a causal path. So Z with U and B meets the adjustment criterion. What did we learn from this example? Well, it shows some interesting facts about identification by adjustment. First, not all available variables should be considered for adjustment. Nodes T and C lie on the causal path. Adjustment for them will intercept the total effect. We will return to this in a future lesson. That'll be on mediation analysis, which has a different goal. It decomposes the total treatment effect into direct and indirect effects. Back to this lesson, we don't adjust for collider. It will make treatment and outcome dependent, even if they are unconditionally independent. Regrettably, it's a common practice to adjust for immediate causes of outcome. Our example shows it'll open the non-causal path. If anything, here is the safe option: condition on the parents of treatment. In this video, I talked about a quantum leap in causal reasoning. You learned about 𝗕separation and identification criterion, how to read dependencies of the graph, all implied marginal and conditional dependencies. You learned the rationale of the identification criterion. If we block all non-causal associations between treatment and outcome, then we reason the remaining association is causal. We conclude we can identify treatment effect. But you learned more than that. Treatment effect is identifiable by conditioning on variables that 𝗕separate outcome from treatment. To recap, conditioning on adjustment set 𝗕separates treatment and outcome along all non-causal paths, and it doesn't block causal paths. Keep on watching.